Okay, so we've seen that you can solve linear equations using the inverse of a matrix. And for really large matrices, working out the inverse is rather a lot of work computationally. So we're going to see another way of doing this called Gaussian elimination. So a system of equations, a system of linear equations in n variables, x1 up to xn, and the right-hand sides are b1 up to bm, so there's m rows, and the coefficients are a, ij, a11, a12. And the indices are, the first one is the row, it's row number 1, and the second index is a column. The columns correspond to the x's. The system of linear equations in n unknowns. Of course, we generally like to have as many equations as there are unknowns, although often in engineering it's a good idea to measure more things than you want to know. So there's a kind of an extra twist on this that often in practice you'd have more equations than unknowns. When you've got fewer equations than unknowns, then you expect not to have a unique solution. But I mean that's also interesting. If you've got lots of solutions, that might be what you want. The coefficients, the IGs, don't have to have nice whole numbers or fractions, and on a computer we typically be solving this using floating point arithmetic. We can write this as a matrix, and that's sort of the part of the raison d'etre for matrices. You pull out all the coefficients, the a's, into a big matrix A, n columns and m rows. In this case, if it's square, m and n are the same, and it's a square matrix. And then we've got the unknowns, a vector of x1 up to xn, and the right-hand side a vector of b1s up to bn. N equations in n unknowns. And then we have to solve ax equals b, and of course, as long as the matrix A is non-singular, then you can just use A inverse, and x is A inverse b. So as long as you know the inverse, you're sorted for any kind of right-hand side that you want to put in b. So here's a little quick example. 3, 2, 7, 5 is our matrix. I'm pretty sure that's non-singular looking at it, right? Because the equations are not multiples of each other. We write down the linear system by just pulling the numbers out and putting them in a matrix. Notice that the x's go in a row, and of course a column, and of course those x's are the headings really for the columns in the matrix. In other words, the x1 goes with the 3 and the 7, and the x2 goes with the 2 and the 5, which is kind of partly how matrix multiplication works. The 3 goes with the x1 and the 2 goes with the x2. So if we want to solve ax equals b for the variable x, first we work out the inverse. So we do that by working out the determinant. Of course, that's 15 minus 14. So it's just 1 and the determinant's easy. And then we swap the 3 and the 5 and negate the 2 and the 7. And then we can solve it simply by applying this inverse matrix to our particular right-hand side 1, 2. So x1 is 1 minus 1. Once you've got that answer, you should just substitute it back in the original equations. And of course, 3 minus 2 is 1, and so on. So it's quick to put it back in and check that it works. So there you go. Ax is equal to 1, 2, which is b. Okay, so this is expensive for large matrices, and it's important to have an efficient method. You also need to spot that the matrix is singular, and for large matrices, even working out determinants is rather a lot of work. If there's no solutions, I mean, for example, in the case of 2 equations, the lines might be parallel, or there's infinitely many solutions if the lines are just multiples of each other. So for large problems, we need a different way because the number of floating point operations, so teraflops is a tera floating point operation for a second. Doing it the way that I've shown, 100 by 100 matrix would take, well, I guess longer than the projected age of the universe when it ends. So we can't do it that way, and we need a much more efficient way. 100 by 100 is a small matrix for engineering problems. So we routinely deal with matrices that might have tens of thousands in either direction, although a lot of zeros. For example, in a finite element simulation in electromagnetics in 3D, large matrices are common. So we can't just do that. So what are we going to do? Well, in the next video, I'm just going to show you the simple example where we solve a 2 by 2 by the usual kind of subtracting so many of one row from the other, and that's the method we're going to formalize to make the method we call Gaussian elimination.